The most visible result of the use of linear algebra might be computer imaging and animations. Linear algebra is what makes 3D animated worlds and CGI come alive. Every explosion, camera pan, or animated character is built on matrix math. In fact, the reason that graphics cards are so important in video games is that they do matrix multiplication thousands of times per second. Why does that matter? Because every time you move around in a 3D world, the computer has to do a bunch of matrix operations to figure out which pixels in the 3D world show up where on your 2D screen. This is the same problem that 3D printers and animating software have to solve. How do these softwares decide what to display on each pixel of your screen when all it has is a web of 3D points to work with? The answer lies in matrices. And in this video, we'll explore a powerful way to think about matrix multiplication. Multiplication as a transformation. You might remember from an earlier video that even something as simple as ax equals b can take weeks to fully grasp because there's more than one way to interpret the multiplication on the left-hand side. One especially powerful way to think of a matrix multiplication is not as a calculation, but as a transformation, and that's exactly what we're going to explore. In order to understand 3D animation, let's break down the traditional pipeline all your favorite 3D graphics go through. First, every object starts in what's called object space, a local coordinate system where the object is defined as a list of points, often stored as a matrix. The first step is modeling individual objects in this space using tools like Tinkercad or something much more advanced. Next, animators move those objects into world space, where they're scaled, rotated, and positioned relative to other objects in a scene. While drag and drop might make this feel simpler for the user, the computer is still thinking of these objects as lists of points or a matrix, so it needs to use matrix operations to transform those points in a way that matches the animator's vision. Once the scene is built, a virtual camera is introduced and everything in world space is transformed again, this time relative to the camera's position and perspective. Next, the computer has to project the scene, mapping 3D coordinates onto a 2D viewing plane, deciding which objects are visible and which are hidden behind others. This process demands massive real-time matrix computation from the graphics card. And finally, the projected view is converted into screen coordinates so your monitor knows exactly what to display in each pixel. What I think is crazy is that every time you pan or zoom on 3D objects on a computer, or move a player or change camera perspective in a 3D game, the computer has to go through the bulk of this process again, either 30 times per second or sometimes 60 times per second. For the rest of this video, we will just focus on the process of going from object space to world space. So how can we find the right matrices that do our desired transformations to transform our object to world space? Here's a very simplified Millennium Falcon. I've made an Excel from a list of points we can think of as a matrix. This ship currently lives in object space, and I want to move it into this scene with asteroids oriented like this. How can we do that? Well, we could start by experimenting with matrix multiplication. We could pick a vector in a matrix and just start changing values to see what happens. We could experiment to see if we can reflect the vector across the x-axis, for example, or rotate a vector 90 degrees. But now you might have some questions like, if this matrix transforms this vector by rotating it 90 degrees clockwise through a multiplication, does the matrix rotate any two-dimensional vector the same way? Or is there always a matrix and a set of matrices and operations that could transform a given vector into a desired vector? Is there a better way than experimenting to find the transformations we want? We won't take the time to go deep into each of these, but to get a handle on the first question, we can keep the matrix the same and change the vector. Does it look like each non-zero vector is rotated 90 degrees clockwise? It sure seems so. We can think about this matrix as not just transforming a vector, but the entire plane. This is often illustrated by using an image on the plane and showing both the transformed image and the original image. This extends to higher dimensions as well. A single matrix will do the same transformation to the entire 3D space or hyperspace. For the second question, there's always a matrix operation or a set of matrix operations to transform one vector to another as long as they're both in standard position. With matrix multiplication alone, we can do a lot: scale, rotate, reflect, shear, and project. But we can't translate since a matrix times the zero vector is always the zero vector. Instead, we use matrix additions for translations. Now the big one. Isn't there a better way than experimenting to find the transformations we want? Yes, there are a couple of strategies. Suppose we want a matrix we can multiply by 1, 2 to get the vector -1, 5. Well, first we can pick arbitrary values for our matrix and set up an equation, like this. We won't find specific values, but we will get relationships between the variables that will restrict values we could use, and then we could pick any values that make the equations true. But there is a more powerful way if we're just working with transformations that can be done with matrix multiplication. We can use standard basis vectors. These are the vectors 1, 0 and 0, 1 in 2D, or 1, 0, 0, 0, 1, 0, and 0, 0, 1 in 3D, and so forth in higher dimensions. There's a simple but powerful theorem for building transformation matrices. If you know how a transformation affects the standard basis vectors, then those transformed vectors become the columns of your transformation matrix. Suppose we want to stretch the plane vertically by a factor of 3 and then rotate it 45 degrees counterclockwise. To build the matrix, we apply that transformation to the basis vectors 1, 0 and 0, 1. The vector 1, 0 isn't affected by the vertical stretch, so it stays 1, 0. Using trigonometry, a 45-degree rotation becomes square root of 2 over 2, comma, square root of 2 over 2, and that's the first column. The vector 0, 1 stretches to 0, 3, and then rotating it the 45 degrees, we get -3 square root of 2 over 2, and 3 times the square root of 2 over 2, which becomes the second column. Now we have the full transformation matrix. This is so powerful, but why does it work? Because every vector in the plane is a unique combination of the basis vectors, and matrix multiplication preserves how those combinations behave. So if we know how the transformation moves the basis vectors, we know how it transforms everything else. Another way we could have transformed this matrix is by multiplying our scalar and rotational matrices first into one grand transformation matrix. But before you start multiplying things willy-nilly, remember that order matters. Scaling then rotating gives a different result than rotating then scaling. This is a great example of why matrix multiplication isn't commutative. The product we want is the one with rotation on the left and scale on the right. That might seem odd, so you're wondering why that order. Well, in English and a lot of cultures we are used to reading left to right, but notice the vector we transform is on the right-hand side, so the first transformation matrix needs to be next to the vector, then the next transformation to the left of that. You can find the form of specific transformation matrices through an internet search. We won't go into each of these here. You can create more complex transformations through multiplying the matrices of the different transformations in the correct order. Now, not every transformation is possible with matrices. For example, this swirling distortion that curves straight lines isn't a linear transformation, so no matrix multiplication can create it. That's because linear transformations take a line to a line, a plane to a plane, or transform them to lower dimension linear objects. For example, planes could go to a plane, a line, or a point, for example. Now let's use what we've learned to get my Millennium Falcon into my world space. We learned that transformation order matters, and so we want to do the transformations to get the Millennium Falcon into the right location, the right orientation, and the right size without one transformation messing up the previous ones. It seems like translating to get it into the right spot should be the last one, because if we try rotating or reflecting, or even scaling after moving the ship, then it could change the location. So let's scale it to the right size, rotate or reflect it to get it into the correct orientation, then shift it to the correct location. I want it half the size that it was in the object space, so I could multiply the matrix of points by 0.5 as a scalar multiplication, or I could use a scaling matrix where I have 0.5 down the diagonal. Next, I want the ship rotated 45 degrees counterclockwise, and we can use our strategy with our basis vectors earlier to find this matrix. Finally, I want to translate it over 2 units and up 3 units. I can make this transformation by adding a matrix that has 2's in the x column and 3's in the y column. Voila! Our Millennium Falcon is ready to escape asteroids. I did this effect simply by repeatedly adding small translation matrices to the object matrices in the world space. Alright, let's take a step back. Thinking about matrix multiplication as a transformation is a powerful way to deepen our understanding of linear algebra, especially as we approach concepts like determinants, eigenvalues, and eigenvectors. But the transformational perspective is an abstraction that strips away units when working in many contexts. For example, a matrix might transform a vector representing sandwich ingredients, like servings of peanut butter, bread, and jam, into one representing nutrients, like grams of protein, fat, and carbs. Those vectors are totally different units, So putting them on the same set of axes to think of transforming one into the other is confusing because we don't know how to label the axes. But abstraction is what gives math its power. Some experts say that all of mathematics is abstraction. We don't need to think about 3 apples plus 4 apples different than 3 cookies plus 4 cookies once we understand the abstractions of number and the addition operation. Understanding one single abstract structure enables us to make sense of many different contexts that share that same mathematical abstract structure. The YouTube channel 3 Blue 1 Brown has a linear algebra series where all concepts are grounded in the geometry of vectors and matrices with a heavy emphasis on transformations. I encourage you to watch those videos. They don't touch on the utility and power of linear algebra to model the real world, like we try to emphasize in our series, but the 3 Blue 1 Brown series can really deepen your understanding of linear algebra. Thank you for watching. Please subscribe and share our videos. Be sure to follow Math the World on Twitter, Instagram, and Facebook. Thank you so much for your support.